Welcome to our channel Quaint Cosmos. Today we are going to discuss something about relativistic quantum mechanics. Electrons, protons, neutrons, all these fundamental particles. Again, quarks are there, neutrinos are there. So these particles move at different speeds. Sometimes speeds are very low, such as if you consider the speed of electrons inside atoms, then speeds are low. Or if you consider speed of electrons through materials when current is flowing, so there is a movement of motion of electrons inside the materials, whether it is copper wire or aluminum wire or something else like silicon or graphene. So different cases are there, and in different materials are there, and in different materials electrons move at different speeds. And not only electrons, I am talking about all the fundamental particles right now, whether it is protons, neutrons, neutrinos, okay, or quarks. So whenever these fundamental particles move at different speeds, question is whether Schrödinger's equation, that is known to you, used in quantum mechanics, whether Schrödinger's equation is able to capture all the effects of motion of these particles moving at different speeds. That is the question, and answer to that question is no. When speeds are not comparable to the speed of light, in that case Schrödinger equation is sufficient to capture all the effects. But when the fundamental particles, or any particle, whether it is fundamental or not, if particles move at a speed close to the speed of light, in that case Schrödinger equation cannot capture all the effects, and in that case you must take into account the relativistic effect. So you know that Einstein gave us in 1905 one theory known as the special theory of relativity. So that effect, special theory of relativity, you know that thing, and that effect must be taken into account while considering the motion of particles moving at speeds close to the speed of light. So here in this lecture I am talking about only the fundamental particles. Okay, so relativistic effect is required. Okay, so Paul Dirac, he discovered an equation known as Dirac equation. That equation is famously known as Dirac Equation. In 1928 he discovered. He actually set out to solve this problem of relativistic mechanics. Okay, means he combined the idea of relativity and this motion of fundamental particles. Means he combined actually special theory of relativity and Schrödinger equation. And therefore he discovered a new equation known as Dirac equation. You can see the equation on the screen. So here you can see that I gamma mu del mu minus m into psi is there. What is m here? M is the mass of the particle. Psi represents wave function, and gamma represents special matrices known as gamma matrices. Okay, and the first term, which is I gamma mu del mu, that represents actually that energy momentum relationship. Okay, so this is the Dirac equation. This is the Dirac equation, and the algebraic form of the equation in a special case, it is equal to E square. E square is equal to P square C square plus M square C to the power 4, where C represents a speed of light in vacuum. Okay, M is the mass of the particle, P is the momentum of the particle, and capital E, which represents energy of the particle. So you can see this equation. If you talk about only this algebraic equation, then you can see that E square is equal to P square C square plus M square C to the 4. So what is the value of E? Then E is equal to under under root of plus minus under root of p square c square plus m square c to the power 4. Plus minus sign is there. So negative energy states exist. You can see here. E is equal to plus minus, then under root quantity is there. So plus minus exists. So E is equal to plus something means E is equal to a non-negative quantity that is known to you. That really exists. But E is equal to negative quantity. What is the meaning of that thing? And according to Dirac, it represents some other particles. These negative energy states, some other particles. Later it was discovered that for electrons, these negative energy states actually denoted what? Positron. Means positively charged electrons. That means the idea of antimatter came out from this equation. Not for all the cases this happens, but here in this special case, those negative energy states actually revealed the existence of antimatter, and in case of electrons, these antimatters are known as positrons. Okay, again if you talk about electrons moving inside graphene material, graphene, okay, you know that graphene is a single layer of carbon atoms, and structure is like honeycomb like this structure exists. Okay, so there electrons move when electric field is applied, and in that case using the Dirac equation we can easily explain that electrons mass can be assumed to be 0, and really practically we have found that thing, because the motion of electrons in graphene does not depend on electric field being applied. It's actually a constant velocity known as Fermi velocity, which is equal to 10 to the power 6 meter per second, just 1/300th of the velocity of light. Velocity of light is 3 into 10 to the power 8 meter per second, and here in this case the Fermi velocity means velocity of electrons inside graphene material is 10 to the power 6 meter per second. So if you take the ratio, it will become 300. Means take the ratio of speed of light in vacuum and Fermi velocity, then that ratio is equal to 300. So since it is a 1/300th speed of the velocity of light, that means this speed is comparable to the speed of light. So here in this case you need to consider mass of the particle. Okay, you need to consider mass of the particle. Very high velocity is there, but special case occurs in case of graphene. What special case? Dirac cone is there is a formation of Dirac cone, and due to the presence of that Dirac cone, the electrons behave as massless particles. So if you use the equation, the same equation, E square is equal to p square c square plus m square into c to the power 4, then you can see that you just put m is equal to 0 in that equation. So you are getting what? You are getting E square is equal to p square c square, and therefore you are getting E is equal to pc. Means energy is equal to momentum multiplied by speed of light, and which is also applicable for photon, that is light particles. That means we can say here at this point that movement of electrons inside graphene material behave same as photons. You know photons are massless. That's why E is equal to pc. Mass is not present in the equation. Energy depends only on the momentum of photon particles. Mass is absent. Photons are massless. So for electrons inside graphene, same thing can be applied. That's why we say that electrons inside graphene material behave same as photons. Though speeds are different. Behave same as photons, that doesn't mean speeds are same. Speeds are different. Okay, speed of electrons inside graphene is what? It is 10 to the power 6 meter per second. but for photons it is, in vacuum it is 3 into 10 to the power 8 meter per second. Anyway, so that means by using Dirac equation, the idea of antimatter came in the mind of the physicist. Especially I should talk about Dirac. He actually proposed that idea, and later in 1932 positron was really discovered. Though the equation was discovered in 1928. Anyways, that means so in the field of fundamental particles, whether it is particle physics, you know, a standard model of particles exist in particle physics, then in that case this equation is applied, Dirac equation. To study material science, this equation is required. And to study other phenomena where these fundamental particles move at tremendous speed. But for large objects, Dirac equation is not used. Large objects, okay, like planet Earth, means planets, stars, etc. For large objects. In the quantum world, Dirac equation is used because Schrödinger's equation is required. But for large objects, okay, Dirac equation is not used because there you would not, you wouldn't find any effect of quantum mechanics or quantum effects. So only relativistic mechanics is used in that case for large objects. Okay. Here in the title you can see that here in the discussion you have seen that massive particles I have mentioned, but here massive particles doesn't mean the stars or other planets like that, or any object which is visible to our naked eyes, not those objects. Here massive particles means fundamental particles, but where the masses are required in the calculation. Those particles are denoted here as massive particles, and massless means where mass can easily be neglected, there will be no problem at all in mathematical calculation. Anyway, so this was all about today's topic. Actually the topic was what? Topic was Dirac equation. Okay, Dirac equation. And when it is required? When fundamental particles move at incredibly high speed. The speed which is comparable to the speed of light. Only in that case. Okay. Anyway, so this was all about today's topic, and this is the end of this video. Thank you. Thank you for watching this video.